Okay, before I conclude the Newton codes method, some things that you need to know. Alright, if you look at this integral here, in order to evaluate this integral, you need to know a few of your previous values. But if you remember, in most of our problems, we don't know that many values. We only know usually we are only given the value at the initial stage. Or for this case, this would be y at x equals to 0. So we only know one single value. So this means that the the Newton codes method, it is not self-starting. So when I say not self-starting, you cannot solve this method directly without doing any initial work. So in contrast, the other one-step method like your Euler method, your Horn's method, as well as your Runge-Kutta method, you can apply them directly knowing only one single value from your initial condition. Okay, so what happens if you're given this kind of problem and you're only given an initial value? The question is, can you still use the open Newton codes method to solve this ODE? The answer is yes, but you would need to do some initial preparation. So what you need to do is basically you can use your one-step method like your Euler method, Horn's method, but it is always advisable to use the fourth order Runge-Kutta method. So you can use your fourth order Runge-Kutta method to find what is your value at y1, y2, and so on. So let's say let's say we use our fourth order Runge-Kutta method to find out the value of y1. So once we have y1, we can then apply our open Newton codes method by using the rectangular rule. So in this case, we'll have yi plus 1 is equals to yi minus 1 plus 2hf at xi yi. So in this case, your yi minus 1 would now be your y0. Okay, so if I'm going to find my y1, if I'm going to find my y1 would be y0. Sorry, keep getting confused. So if I want to find my because I've used my Runge-Kutta method to find my y1, so the next value of y that we want to find is basically y2. So y2 now would be given by y0 plus 2hf at x1, y1. So the thing that I want to point out is the method is not self-starting. So if you're given only an initial condition, you can do some preparation to find out the values of y for some of the few steps before. And the index that I've used here, yi minus 1, yi plus 1, this is general. Okay, so in the case where you have y0 and y1, this would become y2, and your yi minus 1 would just be y0, and xi yi would just be x1 y1. So what we want to do now is to look at another multi-step method, which is also known as your Adam's method. Okay, so let's consider again the ODE that we have, and you're given this condition. So I can integrate this to give me dy is basically the integral of fxy dx. So what the Adams method proposed is that suppose that we know the value of xi such that we can find the value of yi. What we want to do is to find the value of y at xi plus 1. So this is an unknown value. So when we do our integral, this would be an integral from xi to xi plus 1. And this, the integral would be from yi to yi plus 1. And this would be xi plus 1 and xi. So you can immediately see the difference in the limits of your integral. Whereas in the Newton codes method, you're using all the previously known values. For your Adams method, what you're doing is you're only using the value from your current step. Okay, so if I evaluate this integral, this would be yi plus 1 is equals to yi plus the integral of xi to xi plus 1 fxy dx. Okay, again note that this is now only xi instead of all the way to xi minus n. So what this means is that if this is your function f here and you want to do the integration, unlike your Newton Cotes method where you take all the values previously, what you do is you're only taking this xi value to find out what is your value of xi plus 1. Okay, so to derive the Adams formula, what we want is to use the Taylor series. Okay, so my Taylor series is given by yi plus 1 is equals to yi plus hyi prime plus h square over 2 factorial yi double prime, and then you have all your higher order terms. Okay, since in my ODE my y prime is basically my f, so I can also rewrite this as my yi plus 1 is equals to yi plus hfi Okay, so what I've done is I've just replaced my y prime with my f, such that my y double prime is my f prime. Okay, so we can use finite difference approximation to approximate what is our fi prime. So our fi prime is given by fi minus 1 over h. So if you only take the first three terms in our Taylor series and substituting my f prime here into this expression, what I get in the end is yi plus 1 is equals to yi plus h 3fi minus 1 over 2, and this would have an order of h cubed. Okay, so this is obtained from Taylor series. Now if I write it again just for convenience purposes, so this would be h 3fi minus 1 over 2. Okay, this is from our Taylor series. If you go back to our integral, I have this equation here. So if I write my equation out here, this would be given by yi plus xi to xi plus 1 fxy dx. So matching my coefficient, my variables here, you can see that the integral of your fxy from xi to xi plus 1 is actually given by h 3fi minus 1 over 2. The problem with this is, if you look at this integral here, in order for you to calculate this integral, you're using values from previous values, which means this is identical to the open Newton Cotes method that we have just considered. Okay, because what we are doing is we are trying to find out what is yi plus 1 using values of f at your previous values. So this is still an extrapolation, which means this is an open form of your Adams method. Okay, because it is an open form, we would generally have a larger truncation error. So one way that we can do to reduce this error is to use the value that we calculate here and apply the closed form solution again. So to apply the closed form solution, we again use the Taylor series approximation, but right now we use a backward Taylor series. So I can write it as yi is equals to yi plus 1 minus fi plus 1 h plus fi plus 1 prime over 2 factorial h square, and this would be your fi plus 1 double prime h cubed. Okay, the term backward Taylor series means that what I'm doing is I'm trying to use Taylor series to expand yi by taking yi plus 1 as my base point, such that my h is xi minus xi plus 1, which means my h is less than 0, or it has a negative value. Okay, so again, if I use finite difference approximation to find what is my fi plus 1 prime, this would give me fi plus 1 minus fi over h. So if I substitute this into this expression here, what I'll get is my yi plus 1 after rearranging will give me yi plus h fi plus 1 minus plus fi over 2, and this would also have an order h cube accuracy. Okay, so this is known as your Adams method, your closed form Adams method, and it is used as a corrector step to your previous predictor step. So this open form is basically a predictor, which means I can call this with a superscript 0, and then I can use my closed form method with a superscript 1 to find out what is my yi plus 1. Okay, so if you look at your lecture notes, there are some definitions and comparisons that I hope you'll go through yourself. Also, I've also shown you the third order Newton-Cotes method, which is also known as the Mills method. So the equation that you have in your lecture note is of order h to the power 4 accuracy. Okay, so there are two equations. One is for your predictor and one is for your corrector. Also, you have the third order multi-step method for your Adam-Bashford formula. Okay, so again, these are order h4, and you have your predictor as your corrector as well. The same approach can also be extended to higher order multi-step methods, and if you go to reference books, there are tables that present the coefficients of your predictors and your correctors in your Adams as well as your Newton-Cotes method. Okay, one thing that you need to know: the multi-step method is not a superior method over your one-step method. It just offers an alternative to your Runge-Kutta method. Okay, when you compare the Newton-Cotes method to the Adams method, the Newton-Cotes method is generally more accurate, but it is less stable. So there is an example in your lecture notes in slide 35 that if you solve it with your third order Mills method and your Adams method, you can see that the Mills method, which is your Newton-Cotes method, is less stable. So that's it for lecture 17. Most of the definitions and comparisons are described in your lecture notes. So in addition to this recorded lecture, please go through the lecture notes.